Alright, hi. I'm Aaron Sipe, and I was doing a pretty simple circuit design that would allow two LEDs with one of them to be much dimmer than the other one. My design has one singular 100 ohm resistor, a 1 millihenry inductor, then my voltage source is two batteries connected in series to add up to approximately 3 volts. As you can see by the design, it is very simple with just the inductor and the resistor in series with another LED, and then that entire series is parallel with another LED. The switch is at the front of the whole circuit, which is directly connected to the voltage source. Here I was saying that in order to calculate any of the currents running through the circuit, you have to calculate the resistance of the LED. Those values can be found on the spec sheet of the LED, and that will allow you to calculate the resistance from that. That resistance is used in this slide where I was using mesh current analysis with the circuit combined, put into the configuration as shown with loop 1 being on the left, loop 2 being on the right. Starting with the voltage source being negative Vs, then the inductor can be ignored since there's no timer to change of current. So that means there's no voltage drop through the inductor. Therefore, the only voltage drops you have to worry about is the resistor and then the diodes. So loop 1 is the voltage source, negative voltage source plus the voltage drop through the first resistor, a 100 ohm resistor, then the voltage drop through the 10 ohm resistance of the diode. Loop 2 is very similar, just the opposite for the diode and the resistor. And then since the second diode has opposite orientation as the first one, that will also be negative. And using KVL, both those have to be equal to 0. Simplifying those and using Ohm's law, you can find that the source voltage will equal 110 times the first current, the current in the first loop. And for the second loop, it'll be 10 times I2 will equal negative of the voltage source. Doing that, we'll find that if using the idealized value of 3 volts for the voltage source, you'll find I1 to be approximately 0.27, 0.027 or 0.03 amps, then I2 will always be 0.3 amps with that, or negative 0.3 amps using that using that 3 volt value for the voltage source. Here I can show that I put everything in the MATLAB so you could have the variable voltage source measurement using the multimeter. In my design of this, I just used 3 as the idealized value to make everything simpler, make the numbers easier, but that will change depending on the charge left on the batteries. Then in order to check the work of using MCA, I used NVA here, and in order to do that, I had to find the total source current, and to do that, I had to find the total resistance of the circuit. And to do that, I just treated both sides of the circuit as resistors in parallel, since the inductor can be ignored again because there's no timer to change the current. So doing that, we'll find the total resistance of the circuit to be 9.17 ohms. So the course current will always be the voltage source divided by that 9.17 ohms value. And using NVA, there will only be one node that is of relevance other than ground, and that will be node A, which is at the top center of the circuit. Go back to here, it's the one right after the switch. So now the only equation for NVA will be source current will be equal to the current running down the middle branch, and then the current running to the right. The source current, as mentioned, is the voltage source divided by 9.17 ohms. And since ground will be the only other node of relevance here, current 1 will be 0 minus VA over 110 ohms, which is just the resistor plus the diode resistance. Then on the right side, we have I2, which will be 0 minus VA over the 10 ohm resistance of the diode. If you've worked this out, VA will be exactly equal to VS, which is what you expect, with no resistance between the two. And then I explained that the inductor can be ignored for most of these calculations since there is no timer to change of the current.